Okay. So, we have already looked at limit definition of a derivative at a point. So we looked at this Desmos graph here, and the idea was that we had 2 points, and we were approaching whatever value this was right here. This a, f of a, was a fixed point that we knew. So like on your graph, like on the example we did, it was the point 0, 0. We knew where it was at, and so we took this point and we moved it closer and closer and closer and closer to that point, and it gave us a tangent line at that, or the slope of the tangent line at that point. Okay, so that was our idea. This x approached a. So we today, at the end of the notes on Thursday, the last thing we did is I gave you like 3 different problems all for the same equation, right? And so we had to do that limit definition of a derivative 3 times. But there are a lot of cases where we need to do the limit definition, or we need to do that derivative multiple times. So today what we're going to look at is a way that we can find the limit definition of a derivative in a general form, and then we can just plug numbers into that derivative. Okay? So it's similar to what is happening here. So notice here, make this zoom this in a little bit. All right, so I've just got a function, and instead of calling this x f of x and a f of a fixed point, I have called this x f of x and x plus h f of x plus h. Okay, so this green bar right here represents the length of h, right, however far. So if this is x f of x, and then this is your x coordinate that you're dealing with here, it would just be x plus whatever that h value is. All right, so if I want to find the limit definition of a derivative, as I get closer and closer and closer here, it approaches a tangent line. Okay, the picture looks basically like what we were dealing with before. I've labeled things different. But as that happens, so if I start anywhere over here, as I take this point that I have called x plus h, f of x plus h, as I get closer and closer and closer to that point that I'm thinking about, what's happening to my h value? Smaller and smaller and smaller. What is it approaching? It is approaching 0, right? That h is the distance between your 2 points, your horizontal distance between your 2 points. So as that gets smaller and smaller and smaller, you approach your tangent line, right? So this is what we're going to use today, and once we've done a few, we'll see the benefit of using this versus the other definition that we have also used. You will need to know both of them. Both of them will be asked for. So, oh wait, I need to write this here. So, let's go ahead on these notes. Let's write them both down. So, at a point, that was finding the slope between a, f of a, and x, f of x, right? And so our limit definition of the derivative was that f prime of a, that means the derivative where x equals a, was the limit as x approaches a of f of x minus f of a over x minus a. That's the one that we already did. It gives you the derivative at a specific point. So at x equals 3 or at x equals 7. right, at one specific point. Okay? The one that we're going to do today is going to give us a general form of a derivative. So I'm going to call my points x, f of x, and then x plus h, f of x plus h. Right? So if I'm doing the slope between those 2 points, right, it's y1 minus y2 over x1 minus x2. So I would do f of x plus h, that's this y coordinate here, minus f of x over x plus h minus x. And I would want to do the limit of this as, no, not as x approaches something, but as h approaches 0, because h is that distance between the 2 points, and we want that distance between the 2 points to go to 0. Now, I could simplify this a little bit, because do you guys see anything particularly in the denominator here that could simplify? What would happen, Grace? The x plus h minus x, what would that be whenever you put stuff together? It's just h, right? Because this x right here is going to cancel with that negative x right there. So we could simplify this a little bit. Limit as h approaches 0 of f of x plus h minus f of x all over h. And this is going to give us f prime of x. Okay, so this is the one that we're working with today. Both of these we need to have memorized. Okay, so both of these we need to have memorized. But this one is at a specific point. They've told us x equals 3. This one is a general form. They did not tell us the point that we need to find the derivative at. Okay, so let's see what this looks like here. Let's do a problem. Because at this point, it may still seem like jumbled nonsense of crazy letters, right? So I'm going to write down that. Limit definition of a derivative again, just so I've got it on the same. I always want to use a X right there. Okay, so the derivative, which is also just another name for the slope of the tangent line, at x. This one just says find the derivative. It does not say find the derivative of f of x at x equals 3. Right? It doesn't give us a specific point. So we have to use this form because we don't know a specific point. So we have to first find f of x plus h, right here. So whenever we see f of x plus h, that means to plug x plus h into the f function, where the x is at, right? So for this one, it would look like this, x plus h squared. Right, we're plugging x plus h in for the x right there in the f function. So we are going to have the limit as h approaches 0 of x plus h squared minus, right here, we have f of x. What is f of x? It is x squared, so we put x squared here. The bottom is just the h. Okay, so I will have, if I square this, I square double square, I'd get x squared plus 2xh plus h squared minus x squared all over h. What is going to happen with my x squareds there? They're gone. They cancel. So I've got limit as h approaches 0 of 2xh plus h squared all over h. What do I have to do now? Pull out a h. Now my h's can cancel. And I need to, at this point, once my h's cancel, I need to plug in 0 for what? H. Not for the x, just for the h. So I get 2x plus 0, which of course is just 2x. So what I have found is that f prime of x equals 2x. Yes. Yes, that this f prime of x right here is the derivative. Yes. So here's what this gives us. Right, this is slope of a tangent line. So what this gives us is slope of a tangent line at any point. It's a formula we can use to find the slope of the tangent line at any point. So like that last problem that we did on the notes the other day, if we had done it this way, then if I needed to find f prime of -1, I would just do 2 times -1 and get -2. If I need to find the slope of the tangent line at 3, I would do 2 times 3 and get 6. If I need to find the slope of the tangent line at -5, right, I would do 2 times -5, and it would be 10. There. Slope of the tangent line. And let's think about it on a graph here.
So the slope would be -2, and the slope would be 6.
Yeah. So let's, let me do a new graph. So, like, we're looking at just the basic f of x equals x squared. Oops, not that. There we go. F of x equals x squared, right? So if I do, let's see, I need to do let's see. I need to do y equals a times, or m times x minus a, plus f of a. You don't necessarily have to know how to do this, I'm just programming it, so actually let's just do add slider. Okay. Oh. A. Okay. Alright, so if we want, like I said, at the point -1, right here, if a equals -1, right here, then the slope of that line, -1 times 2, you can see that slope of that line is 2. If I move this point over here to where a equals -3, right? Now the slope is still negative but more steep, right here at this point. And you can see 1, 2, 3, 4, 5, 6 over 1, so have a slope of negative 6. And then if I want to see over here at, 2, right here at 2, my slope would be 4, right, up 4 over 1. So this equation right here gives you the slope of that tangent line at any point. Okay, so it is helpful. You could, well, you have to know both of them because the way they word the questions on the AP exam, a lot of times it's not the answer, it's the set up the limit there. But if we only knew one of these, we could get by with never learning the first, other than the fact that AP is going to ask us questions that make us know that first one. We could get by with never learning how to do it the first way, by only doing it this way and then just plugging in a number. So we could get by without ever knowing the stuff from 2.1. Although AP's not going to let us because they want you to know that definition too. I think the limit is harder to find with these problems, but once you get it, it's much easier to use there. So this is just a different approach. They'll give you that general form. Okay? And you have to do this if it just asks you for the derivative and not at a specific point. Okay, let's try another one. I never did teach you this shortcut. Okay, let me show you the shortcut. All right, so if there's maybe on the back of your sheet there, Pascal's triangle. I was going to do this for a warm-up one day. I see in my problem there I've got x to the third power. And I'm already thinking that doing x plus h to the third power sounds terrible and I don't want to do it. So there is a shortcut we can use involving Pascal's triangle. Pascal's triangle looks like this. It has a 1 at the top. Then it has a 1 here and here. And then every line after that, you're going to have 1s on the outside. And then to get the number here, you're going to add the 2 numbers in the line above it. So that 1 plus 1 would give you 2 here on that line. And then so to do the next line, you would have a 1 here and a 1 here. And you would add 1 and 2 together and get 3 for a spot here. You'd add 2 and 1 together. You would get 3 here. And then we could keep going. We could add 1 and 3. That would give us 4. We could add 3 and 3. That'll give us 6. We can add 3 and 1. That'll give us 4. All right, and you could keep going. I'm gonna do one more line just to show you. 4 plus 1 is 5 here. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. So Pascal's triangle can be used as a shortcut to expand binomials. So this is what you'll get if you have the 0 degree. So think of a plus b to the 0 power. Anything to the 0 power just gives you 1, right? If you have a plus b to the first power, or first degree, that would be the second line. Which, if you have a plus b to the first power, it's just itself. So both of these are 1s. If you have a plus b squared, second degree, that's this next line. We don't ever really use Pascal's triangle for these first 3 lines because we don't really have to do much there, and you guys know how to square double square, right? But past second degree is when this starts to be useful. So if I have a plus b to the third that would go for that third line, a plus b to the fourth, and a plus b to the fifth. And then this is infinite. It keeps on going forever, but you're probably not going to see anything that goes beyond fifth power, I would not think. So let's look at how to use this, because that still doesn't tell you much about how to use it, right? So if I have something like, let's say that we need to find x plus 1 to the third power. Okay? The way that we use Pascal's triangle is if we've got something to the third power, we are going to use the fourth line right here, 1, 3, 3, 1, the one that's for third degree, right? So we would have 1, I'm going to leave lots of space, 3, 3, 1. Those are going to be our coefficients. And so what we would do is we would start with our x's. So we take whatever this is right here, and it's going to be x to the third power here, x to the second power here, x to the first power here, and then x to the 0 power here. And then for the second part, I'm going to take whatever number I have here, really the positive one should go with it, and I will have 1 to the 0 power, 1 to the first power, 1 to the second power, 1 to the third power. Put just some plus signs in between. So whatever this first term is, whatever your degree is, you start with the highest and then you descend, right? 3, 2, 1, 0. And then you take your second term, whatever that is, and you increase 0, 1, 2, 3. So if we simplify that down, we just get x to the third here, plus, all these being 1s really simplifies this one because all those 1s, those different powers. So we get plus 3x squared plus 3x plus 1. Now, because that was a really simple one and we just had 1s there, it made it a lot easier to expand there because all these 1s just stay 1s. So you just basically have the coefficient and then the x's are descending. Okay, questions on that? We'll do another one. All right, so let's do one that's harder. Let's do this one. 2x minus 3 to the fourth power. So think about what you would have to do this without using the shortcut. You would have to write 2x minus 3 4 times, right? And then you would have to multiply like each set together and then multiply those two together. It would take a long time and it would have a lot of room for error. The shortcut makes it a little quicker on this. So I would have my coefficients are 1, 4, 6, 4, 1. I'm using that line for the fourth degree. It's the fifth line on your triangle. Alright, so this time I don't have just an x, I've got a 2x. So I have to do 2x to the fourth, 2x to the third, 2x squared, 2x to the first, and then 2x to the 0, but that's really just 1, so if you want to leave it off, that's fine. And then I'm going to take this -3 right here, and I'm going to have -3 to the 0, negative 3 to the first, negative 3 to the second, negative 3 to the third, and negative 3 to the fourth. So this one's a lot harder, but let me tell you, this is still easier than expanding all the way. So if I've got 2x to the fourth, 2 to the fourth is going to give me 16. So I'll get 16x to the fourth. You got a 1 here. Negative 3 to the 0, what's that? It's just 1. So we get 16x to the fourth. Careful with it. So I'm going to have here 4 times 2 to the third, which is 8x to the third, and then times negative 3. So that is going to be, if you get one this big on homework, you have my permission to use the calculator. 4 times 8 times negative 3 is going to give negative 96. So I should, since we get a negative, let me erase that. Negative 96x to the third. Alright, here we're going to have 6 times 4x squared times negative 3 squared is going to give us a 9. So 24 times 9 is 216. So plus 216x squared. Here we're going to have 4 times 2x times negative 3 to the third. It's going to be negative 27. So 8 times negative 27 is going to give me negative 216x. And then for this last one, 2x to the 0 is just 1. So I'd really just have this negative 3 to the fourth. 3 to the fourth is going to be 81. So plus 81. And so that would expand that for us. What we're going to see today is mostly taking x plus h and expanding it, so we're not going to see ones that are as difficult as the 2x minus 3 very often. Okay, does this make sense? I don't necessarily have to teach this to you. You can do it without knowing the shortcut. It just is going to make this next problem easier. So, I don't think I did attendance today. I'm sure one of those emails says, please do attendance. Yep. Alright. Okay. Alright, so I've got x plus 3 plus 2x. So let's remember our limit definition of a derivative. It's going to be limit as h approaches 0 of f of x plus h minus f of x all over h. And so I've got to do f of x plus h. My function, so when I'm doing f of x plus h, my function is x to the third plus 2x. I've got to erase my x and put x plus h in both spots, right? You don't have to write this over to the side. I just want to be clear what's happening there. So we're taking out the x, we're putting the x plus h. So this f of x plus h, it will look like this. X plus h cubed plus 2 times x plus h. That's this part. Alright, then it tells me I need to subtract f of x. So f of x, that is just your function. Make sure when you put this here, you need parentheses around it because it is a minus sign, which has to be distributed to whatever is your x, your f of x is. On the last problem, it didn't matter because it was just the x squared, but here that negative has to be distributed to both these. And then this will all be over h. So to expand x plus h cubed, I can use that shortcut. So the coefficients for that third degree line are 1, 3, 3, 1. So I'm going to have 1, 3, 3, 1. And then it's going to go x cubed, x squared, x to the first power. I'm not going to write my x to 0 right there just because that way I don't have to, write another step where I simplify. Then I would have 0 h's, 1 h, 2 h's, 3 h's. And we're going to put plus signs in between those here. That is only expanding that little part right there. So I still have this 2x plus h. I need to distribute that too. So I get plus 2x plus 2h. And I need to distribute the negative here. So I get minus x cubed minus 2x. Is everybody with me here? Questions? All right, so what should happen on the step is anything without a h should cancel. If it doesn't, you've probably multiplied something wrong or plugged something in wrong. So I've got an x cubed right here. It cancels with this x cubed. I have a 2x right here. It cancels with this negative 2x. And so I'm going to write that as a little note over here. All terms without an h should cancel. Right? If they do not, then you have probably made a mistake somewhere. So if all of my terms that I have left, so if all 4 of these terms that I have left have an h, which they do, what can I do with that h? Pull it out. So I'm going to pull an h out. So we'll have 1 less h for each term. So that's going to be 3x squared plus 3xh plus h squared plus 2. Okay. Now my h's can cancel. So what should happen on all of these problems is that you should have all of your x's cancel. You should have an h you're able to pull out. The h's should cancel, and then you could plug in. And so once we do that, we are plugging in 0 for what? H. So we will get 3x squared plus 3x times 0 plus 0 squared plus 2. And so 3x times 0 is just 0. And 0 squared is just 0, so we just get 3x squared plus 2. So f prime of x equals 3x plus 2. Yes? This one here. No. Here. Yeah, the x cubed canceled with this x cubed over here. Okay, questions? And so if you plugged in 1 into this, it gives you the slope of the tangent line at 1. If you plug in 0, it gives you the slope of the tangent line at 0. If you plug in 52, it gives you the slope of the tangent line at 52. I'm going to give you this hint. Not hint. Just going to tease you just a little bit. I could have told you at the very beginning of this problem, before I did anything, that the answer to this was 3x squared plus 2. I knew how to do it without doing anything. So while we are going to have to do this, and while we do have to learn it this way, a shortcut is coming. You may even want to be thinking about what that shortcut is. However, you can't use it yet if you do figure it out. Okay? You have to do the limit definition of everything. Your homework has to have a limit definition on it, because they do ask these problems on the AP exam, and they ask it in a way that you have to know that it's limit definition. You have to know the limit definition of a derivative. Not a ton of it on the exam, but they are on the exam. So we have to do it. Now, I do know how to do this one without, I do know how to do this one also without doing limit definition of derivative, but not as quickly, and it's a different shortcut rule. All right, so this is new notation here. Whenever we see d over dx of bracket and we got something inside, this means the derivative of whatever is inside. So if it was like the problems we had done before, they'd tell us f of x equals square root of x plus 1, and then it would say find f prime of x, right? Those would be the same questions there. So they're asking us to find derivative of square root of x plus 1. We are going to use that limit definition of a derivative with the h. Also, our textbook does not use a h. Our textbook uses a delta x. I know that Raven, when we were doing those delta x problems, you always turned them into an h, right? Because the delta x is more confusing. AP is more likely to use a h, so I'm using that here. But if you do look at the examples in our book for this section, they're going to, instead of using an h, they'll use a delta x. But all those limit problems that we were doing earlier with delta x's that were just like for practice in our book, they were limit definition of a derivative problems that they had just disguised and put in there. You just didn't know it was limit definition of a derivative at that point. So these are like those delta x problems. So we are going to do the limit as h approaches 0 of f of x plus h. So that means we're going to take this equation, and where the x is, we're going to put x plus h minus x, f of x, which is just the function, all over h. So, again, just make sure everybody's with us on where this is your f of x plus h. This part right here is your f of x. And f of x plus h is just plugging x plus h in where the x is at in the function. F of x is just the exact function there. Now, how are we going to do this? We got square roots, and not only do we have square roots, we've got 2 of them, which we don't usually have. But our approach is going to be the same as it would be if we just had 1. What should we do here? Hello.
I
We should compete in this. It could be. Thank you. We do not have any today, but we're going to bring some. Let's not rob anywhere to make this happen. Let's not go Robin Hood on this campaign here, because that will probably get you in big trouble. Huh? I think that we should probably not rob anywhere for this canned food drive. I think that would do more harm than good. Although, let's not. But if we did bring in some canned food, then it would go to people that need it, which would be wonderful. And then we would get Krispy Kreme donuts, which would also be wonderful. Because sometimes with these things, classes do not participate very much. So sometimes it doesn't even take that much to win. So we should participate. Connor, you're not understanding the spirit of this canned food drive. You want to rob the hurricane victims and bring it up here to the food pantry of Elkin. It's just going to delay it. It's just going to swing by Elkin High School to get us. No, they're going to eat the Bush's baked beans. There might be some there's going to be some. I don't know. I think people eat corn. I think it's going to be like the like canned okra or something that might end up in the ocean somewhere. Yeah. So raid your pantries. Make a run to the grocery store. We'll see if we can't bring in a few things. All right. So we need to rationalize this. Now, something you guys are doing a terrible job of on your free response. If you have to rationalize, you need to put me some parentheses around this, and when you multiply, you need parentheses around what you're multiplying by. So x plus h plus 1 plus square root of x plus 1. You need parentheses around that. So far, as long as you eventually got to the right answer, I've not been counting off if you're leaving off those parentheses, but they are necessary. There. Because I will probably also become, just like those naked limits, I'm going to become less lenient on your notation as we go along, because, AP is not very lenient on a lot of things on notation on the free response. And I could be nicer, but if I don't make you do it, then it's going to be hard for you to remember to do it whenever we actually get to the exam. And if I don't take off points for it, it's going to be hard to make you do it. So make sure you're putting those parentheses there. So when I do square root of x plus h plus 1 times square root of x plus h plus 1, I just get x plus h plus 1. And then middle terms will cancel. That's why we use the conjugate. And then I get minus x plus 1. But this is wrong. Right here, what I've written. What do I need? I've got to have parentheses right there. So you either have to put the parentheses or you have to go ahead and distribute that negative. And right here, make sure you put parentheses. It's h times x plus h plus 1 plus square root of x plus 1. Without the parentheses, that is incorrect. All right, so if we distribute this negative here, then that will give us the limit as h approaches 0 of x plus h plus 1 minus x minus 1 over h times square root of x plus h plus 1 plus square root of x plus 1 here. And just like with our other problems, everything without an x should cancel. It does. This x cancels with this x. This 1 cancels with that negative 1. If you see that you got anything left that does not have an h, you probably forgot to distribute a negative or multiplied something wrong. You've made a mistake, right? So we get limit as h approaches 0 of h over h times square root of x plus h plus 1 plus square root of x plus 1. And then the x on top and bottom can cancel. Alright, so I'm plugging in 0 for what? H, not x, h. So I get square root of x plus 0 plus 1 plus the square root of x plus 1. So that is 1 over square root of x plus 1 plus square root of x plus 1. What is square root of x plus 1 plus square root of x plus 1? 2 square root of x plus 1. So my answer here is going to be 1 over 2 square root of x plus 1. And that will be my answer. Alright, we have not gotten to the tangent line problems, and I'm not going to try to cram that in today because it is important. So, we'll finish these notes tomorrow, which means I need to adjust your homework assignments here accordingly. So, let's see. We're going to save this homework assignment. Well, you're still going to have homework, so don't get too excited. But these were all tangent line problems. I was going to teach you how to do the tangent line problem, which involves doing this, but I didn't. So, we're going to save that. We're going to do that, but just not today. And then we are going to do, let's do page 131. We're going to do 15 through 23 odd. Okay. You are finding the derivative here. It's the general form, so you have to use the f of x plus h minus f of x over h for this